So now the rest of the fun for the night here. Talk about myoglobin and hemoglobin. I say for the night, and it's like noon. So I usually do these at night, and we're inside. I can't see sunlight, so hey. So myoglobin. What is myoglobin? What is myoglobin? Don't quite go there. Don't quite go there. But what's the function of myoglobin? How's that? The function of myoglobin is to make turkey and chicken taste good. That's what its job is. So obviously I'm being facetious, but it's myoglobin that causes dark meat to be dark. So your white meat just doesn't have a lot of myoglobin in it. So, but seriously, myoglobin is there. It is for oxygen storage in the muscles. So your muscles, where do your muscles normally get oxygen from? The blood. So, but every once in a while, you might get chased by a lion or something like that. And you need to run really fast, and your blood can't supply enough oxygen to your muscles fast enough. So your myoglobin kicks in and says, oh, we've been saving this for a rainy day or a lion. So, and they kick in and throw in some oxygen that they've been storing for a while. So, but myoglobin has what we call a heme group, an iron-containing chemical structure called a porphyrin, but it has a heme group, and it binds oxygen. So, and if we look at myoglobin, if we look at kind of percent saturation versus the partial pressure of O2, we see that myoglobin gets saturated with O2 very, very quickly. And I say quickly, really at very low concentrations of oxygen. And so it holds on to oxygen very tightly. And the only time it's going to give it up, notice if we're way over here, that's when myoglobin's holding on to his oxygen for dear life. You're never going to pry it out of his hands. It's only when you start getting down here where the percent saturation goes down that myoglobin's actually releasing some oxygen in that case. And so myoglobin's like, as long as you're good and the blood keeps giving you enough oxygen, I'm going to hold on to mine. I'm just storing it. But as soon as all of a sudden you have a big depletion of oxygen by your muscles and the blood's not supplying it fast enough and the PO2 level starts to drop, myoglobin says, okay, I'll start giving you some oxygen now. So it's a great way to store for that rainy day, if you will, as a muscle cell. So myoglobin is a single peptide chain, which means what kind of structure does it not have? No quaternary structure, it's just a single peptide. And it has a single heme group, a single iron-containing group, so it binds one O2 molecule. Cool. And that's what it does. And the only reason we really bring this up is that now we can talk about something much more interesting called hemoglobin, right? So where do we find hemoglobin? So yes, hemoglobin, what is the function of hemoglobin? No. Hemoglobin, as I learned last night, is for making my friend Josh pass out. That is its job. So he sees the side of blood and it's all over. He told this great story about when he cut off the top of his finger and he passed out several times washing it out in the sink. But anyway, sorry, Josh. Hemoglobin is what makes your blood, red in color and all that stuff. The red blood cells contain it, but it's transport of oxygen, right? So its job is to bind oxygen, and hemoglobin is very similar to myoglobin, sort of. So myoglobin is a single peptide. Hemoglobin has 4 peptides that comprise it, and all 4 of those peptides look a whole lot like myoglobin. So it would be wrong to say that hemoglobin is made from 4 myoglobins. That would be an incorrect statement, but hemoglobin is made from 4 peptides that have a lot of resemblance to myoglobin, if you will. And so each of those 4 peptides then forms a tetramer for hemoglobin. And typically, if we diagram this very, very simply, we have 2 alpha subunits and 2 beta subunits to form this tetramer. So these 2 peptides are identical. These 2 peptides are identical. They all fold up, and then they all come together for quaternary structure, giving you this lovely structure. Now, since one myoglobin can bind 1 oxygen molecule, how many oxygen molecules do you suppose hemoglobin can bind? 4. Sweet. So if you look here, so in black here we have the curve for myoglobin. So if we look at here, the difference when we see hemoglobin, so hemoglobin does something more along these lines. So and we say that the curve is sigmoidal. And being sigmoidal here, that's what we use as the evidence for cooperativity. So cooperativity. Now notice we say the word cooperativity, and I like to think, yeah, these guys are just cooperating with each other. So hence the name, but the way this works is that once any one of these 4 subunits binds to O2, it makes the remaining 3 subunits have an easier time of binding O2. Then once you bind that second one, it makes it even easier for the remaining 2 to bind O2. And so what you end up with is a situation where binding one O2 makes it easier to bind the next one, and bind the next one, and bind the next one. So that's called cooperativity. So, and they call it positive cooperativity because it makes it more likely to bind the next one. So there are examples of negative cooperativity out there as well that we're not going to talk about, but this is positive cooperativity in this case. If you look, based on our saturation curves here, who binds oxygen more tightly? Myoglobin or hemoglobin? Myoglobin, for sure. Wait a minute. So what's myoglobin's job? Just to store O2 for a rainy day. What's hemoglobin's job? His job is to keep me alive when there's no lions, just all the time. And so you're telling me that the one that's supposed to keep me alive all the time doesn't do as good a job at binding O2 as myoglobin? Well, that sounds like a problem. So, but it's actually a very good thing, right? So notice myoglobin, I only need O2 for a rainy day. And what tells me I'm at a rainy day is a super low concentration of O2. And that's only going to happen on a rainy day, i.e. a lion chasing me or something like that. So, but hemoglobin, I got a different story. Where does hemoglobin first pick up oxygen? From the lungs. It gets at the lungs. And in the lungs, there's a very high concentration of oxygen. And so in the lungs, we're way out here. We're way out here. And virtually all the hemoglobin picks up oxygen. So, but then they leave the lungs and go throughout the circulation and hit the capillaries. And at the capillaries, the O2 concentration is way lower because it's not the lungs, right? So second part of this, though, is that it turns out hemoglobin is what we call, at least has some allosteric effectors associated with it as well. And so an allosteric effector is when a small molecule of some sort comes and binds to the protein. And it's not necessarily where, in this case, where O2 would bind. It should bind somewhere else. But that causes the affinity for O2 to change. That causes this protein's function to either be diminished or increased in some weird shape or form. That's what an allosteric effector does. And they can be positive or negative, depending on if they increase activity or decrease activity and things like this. So in the case of hemoglobin, his allosteric effectors include both H+, acidity, if you will, and carbon dioxide. So both H+ and carbon dioxide can bind and reduce hemoglobin's ability to bind oxygen. They reduce hemoglobin's ability to bind oxygen. That's what they do, which is a great thing. So because when you go out to the capillaries near all the tissues, they're sitting there doing, glycolysis and TCA cycle over and over again to try and make ATP. So, and the byproducts of all that is H+ and CO2. And so out by the tissues, there's lots of H+, there's lots of CO2, and there's not as much oxygen as there was at the lungs. And so at the lungs, we're way up here on the curve. But at the tissues, the amount of O2 starts dropping down, and then add that to the fact that there's more CO2 and more H+, and the ability of hemoglobin to bind O2 decreases. And so the hemoglobin says, I can't hold on, and it lets the O2 go. And who's happy about that? All the cells out there, right? All the tissues. They're like, great, we needed O2, and you gave it to us. And so that's the great thing about hemoglobin, is if it bound like myoglobin, it would never let the oxygen go at the tissues. But it can bind the O2 at the lungs and let it go at the tissues. It's a great setup. Cool. The other thing it does too is, though, when you get to the tissues, so CO2 and H+ bind allosterically as well, but we can take advantage of that because that hemoglobin's still making its rounds throughout the body, and where's this hemoglobin eventually going to make it back to? The lungs, and it's going to let that CO2 go so that you can exhale it out of your lungs and get rid of it. So it's kind of this great, amazing, multifunctional enzyme here. Main job is, oxygen transport, but other things can be involved. So one thing to note, hemoglobin binds what even better than oxygen? Actually, a lot better than oxygen. Carbon monoxide, CO. Binds carbon monoxide really well. So kind of a problem, right? So if you ever get a carbon monoxide buildup, or like if somebody turns their car on in a closed space, like in their garage or something like that, and just leaves it running. Just thought it was work on their car, and it's just running. So you might get a carbon monoxide buildup, and unfortunately, hemoglobin likes carbon monoxide even more than it likes O2, like a lot more. And so you got a huge problem. All of a sudden, this binds carbon monoxide, and the binding of carbon monoxide makes it so that you can't bind oxygen, and people suffocate. So, and you know what it feels like when you have carbon monoxide poisoning? You just get sleepy, and you fall asleep, and you die. So there's not much of a warning. You can't smell carbon monoxide. You don't sense it coming. You just feel kind of tired, and you're gone. So if you're ever in a situation, where you might be worried about carbon monoxide and you start feeling sleepy, get out right now. So a couple last things about hemoglobin. There's one more thing involved here. So it turns out everything we've talked about with hemoglobin, if that's all the story there was, hemoglobin would still have a curve that fits somewhere closer to myoglobin, somewhere in between. So what's the last thing we haven't talked about? So what is it? So actually, that's a good point, actually. The thing we just talked about with H plus and CO2, that is the Bohr effect, where H plus and CO2 decrease the affinity of hemoglobin for O2. That's the Bohr effect. Thank you for mentioning that. But there's still one thing we haven't talked about. BPG. Sound familiar? So BPG, 2,3-bisphosphoglycerate, is a separate molecule, and 2,3-BPG binds to hemoglobin. So it binds hemoglobin, and it binds it decreasing the affinity of hemoglobin for O2, which is good again. Because if we had a curve resembling more of myoglobin's, the hemoglobin might never let the oxygen go at the tissues. But the BPG decreases his affinity even more so for O2, so making the curve look as it is. Without the BPG, the curve would be much closer to myoglobin's than where it is right now, and it just wouldn't release O2 readily enough of the tissues. Cool. Last thing to note about hemoglobin, I'll just throw a random piece of trivia in here. So if you look at fetal hemoglobin, fetal hemoglobin swaps out two of the subunits that are normally in adult hemoglobin and trades them out for two very, just slightly different subunits we call gamma subunits. And so it's still a tetramer. But it turns out that fetal hemoglobin here, it's got a one amino acid difference from adult hemoglobin. And it's not the only amino acid different, but it's the one that we're going to talk about. This one amino acid that's different makes it so that it doesn't bind BPG so well. And it doesn't bind BPG so well. What would be the effect of that? It binds oxygen better. Fetal hemoglobin is somewhere in between here. So hemoglobin and myoglobin. It doesn't bind BPG so well, so it actually has a greater affinity for O2. Why is that a good thing? Where's the fetus get its oxygen from? From the mother. And so it has to have a greater affinity for oxygen, otherwise it can't take it from the mother, if you will. But once you're born, you stop producing this, and you start producing the adult stuff so you can be, normal functioning outside of the womb. So really nice. Any questions? Let's see if I forgot anything on here. No, that's pretty much what I wanted to say.
The BPG, is that released?
So the BPG, it's something that's inherent in our body. And I say it's inherent. Obviously, everything that's in your body, you either get it in your diet or you make it. But it's something that is currently in all of our bodies. It is there, and it is bound to hemoglobin almost all the time. And so in your body, you have hemoglobin always coupled to BPG. I think the levels of BPG can change when you start getting accustomed to different altitudes and stuff like that. So your levels of BPG can change, so you can change your curve a little bit to match the new altitude and stuff like that. But normally, barring that, I don't know if there's any crazy, syndromes or anything like that where BPG levels will change. So BPG, H plus, and CO2 all decrease the affinity for O2. BPG, you said it does it the best. I would say BPG is the one that's doing it pretty much all the time. Whereas notice the H plus and CO2, when are they causing the hemoglobin to give up its oxygen? At the tissues, but where are they not causing that to happen? At the lungs. And so they're kind of doing it in a cycle, whereas the BPG is just kind of always there in the entire cycle throughout the body.